So welcome to today's session of the Discrete Maths course, Discrete Maths 2 course. Today we are going to complete our brief look at regular expressions, which are the last of 4 different ways that we will see in this course for describing regular languages. Before we do that, before we get to the new topics for today, and in fact, I think that today we will also get started on a fascinating journey to infinity and beyond, which will be in the second part of today's lecture, which will also keep us busy next week, or at least at the beginning of next week. Before we get started on today's topic, let's answer a couple of questions from Dr. X, who has been reading, like you, about regular expressions and is willing to learn more from you about regular expressions. One of the things that he saw was that you can take a regular expression A, and then you can star it to form A star. But actually, you don't need to stop there, because the syntax for regular expressions say, no matter what regular expression you take, for instance, A star, you can star it and get a new regular expression. So A star star is also a regular expression. Question is, what does it mean? What are the strings that match the regular expression A star star? One of your colleagues here is saying, well, this is just another more convoluted way of saying A star. How can we argue, or how can we convince ourselves of whether this answer from one of your colleagues in the lecture room is correct or not? Well, one way to go about it, in fact, the only way to go about it, is to think about what A star star means. That is to say, what does it take for a string to match the pattern described by A star star? So you take your scratch pads at home. We take our scratch pad here, and I cross my fingers, hoping that this will cooperate with me. So we are looking for strings that match the pattern A star star. Okay, so as usual, we follow the good old computer science way of doing things. That is to say, we break up a complex expression into the simpler components, and we try to figure out what they mean, and then from the understanding of the simpler things, we try to understand the more complicated beast. Okay, so if I give you a regular expression, and I say, what are the strings that match the star of that regular expression? What would your answer be? So what does it take for a string W to match the pattern A star star that I have here? So A star star is the set of all strings that you can build by concatenating any number of strings that match the pattern A star. That's what we said last time. Okay, so if W matches this pattern A star star, then it's a concatenation of some number of strings. Let's call them x1, x2, xn, where n can be any non-negative number, particularly could also be 0. And what should be true of each one of these component strings? Each one of them should match A star for all I. That's what I say. So if W matches A star star, if it's a concatenation of some number of strings, each one of them matching A star. That's just the definition of star. Note, in particular, that if n is 0, we are concatenating 0 strings. In that case, W is what? if you write 0 strings one after the other, what string have you written? The empty string, because you haven't written anything. But that's okay, because the empty string always matches a pattern of the form something star. So far, so good. But now we do it again. Okay, when is it that any of these x's matches a star? But what does this mean? This means that each one of these x's can be written as what? As a concatenation of some number of strings that match the pattern A. I see confusion. Okay, so we were looking at a string W that matches this pattern that I have here, the blue pattern. Now, when is it that a string W matches the blue pattern? So let me make this circled as blue. When does this match the blue pattern? Well, the blue pattern is a pattern of the form some regular expression star, where the some regular expression is a star. But it's a pattern, regular expression star. W is going to match that pattern if it can be written as a sequence of strings, each one of them matching what? A star. The red pattern. Okay, but the red pattern is itself of the form regular expression star. So if, say, x1 matches a star, then what do we know about x1? That it can be written, exactly the same reasoning we had before, it can be written as a concatenation of some number of strings, each one of them matching with which pattern? Not really a star. A. So let me use a new color. And let me write this A in this new color, green. Okay, so since x1 matches the pattern A star, x1 can be written as what? As y1, n1, for some number of strings that match the green pattern, A. But the same is true for x2. Okay, so x2 can also be written as a sequence of strings, as a concatenation of a sequence of strings that match the green pattern, A. So let me put indices here, even though I don't particularly like them. It's just that I don't want to get too confused. Okay, so each one of the x's actually is a concatenation of some green strings so this should be an N, which is not particularly right, but anyway, sort of, it's a concatenation of some green strings. Each one of them matches the green pattern, which is A. So what is it that we've done? We've written W as a concatenation of a long sequence of strings. Each one of them matches the pattern A. What does this mean? This means that W matches A star. Which is the reason why the answer that your colleague gave before, namely that A star star is the same as A star, is correct. Let me be sort of more theatrical, if possible. So what does A star star mean? Okay, let's assume that A is some activity, describes some pattern or some activity you want to repeat. A star means repeat A any number of times. A star star means repeat A any number of times and repeat A any number of times. Absolutely, as your colleague is saying, which is the same as repeating A any number of times. That's why A star and A star star are the same thing. Okay? If you're not completely convinced now, there is only one way. Think about it afterwards, later at home. And convince your friends, girlfriends, boyfriends, whatever. Husbands, wives, so you just continue by induction or recursively. Okay? Something more concrete. What are the strings that match that regular expression that you see over there?
2 zeros followed by A0 or A1.
Okay, so your colleague is saying 2 zeros followed by either a 0 or a 1. But there is a star after the 2 zeros. So, okay, we are sort of building towards the answer here. Your colleagues are now saying in the lecture room, as you're probably saying at home as well, and if you're not saying it at home, you should. You can repeat 2 zeros as many times as you want, 0 or more times, followed by a 0 or a 1. Okay, so let's make the explanation shorter. What are the properties of the strings that match this pattern? You're absolutely right. What you said is correct. But let's look for the simplest possible description for this language. What are the strings that match these regular expressions? Okay, your colleague, one of your colleagues is saying odd length. Okay, but in that case, if the string is of odd length, it must have a very special form. Okay. And moreover, it's not all those strings of odd length that we can generate. So for instance, the string 111 with 3 ones is of odd length, but you cannot match that regular, it doesn't match that regular expression. So the string, what form can it have? Odd length of zeros or an even length of zeros followed by a 1. These are the only two things that actually match this regular expression. Because the first start thing says, okay, repeat as many times as you want, write 2 zeros. Which means you start by writing 2 zeros and then perhaps 2 zeros, 2 zeros, 2 zeros. And then after you've done that, either you finish by adding another 0 at the end, which means you have a sequence of odd length that only consists of zeros, or you write a 1 at the end, which means you have a sequence that starts with an even length sequence of zeros followed by a 1. So far, so good? Any doubt about this? If not, we're going to work more with regular expressions right now. So, no. So the question is, isn't the question mark also a regular expression? The answer is, well, in that case, it's a question mark in natural language, and for the syntax that we have given for regular expressions, it's not a regular expression. There are, however, syntaxes for regular expression where it is a regular expression. In that case, I would have to put quotes around the regular expression just to tell you where the regular expression ends and where the natural language question mark begins. You see, natural language can be ambiguous. Regular expressions should not. Well, actually, they are not, because otherwise the machines would get into trouble, even though AI is making great strides. Oh, so the string 1 matches, absolutely. Your colleague is saying, does the string 1 match this regular expression? The answer is yes. Why? Because 0, 0 star can be matched by lambda, the empty string, and then the string 1 matches either you're a 0 or you're a 1. Since this is a concatenation, lambda followed by 1, which is just 1, matches this regular expression, because lambda matches the first part and 1 matches the second. You should feel free to use at any point the fact that if you write nothing and then something, you've only written that something. Lambda followed by 1 is 1, like 1 followed by lambda. Thank you. Keep the questions coming. Sorry, where is my... I didn't do this before, which is boring for those of you who are at home. It's boring for me too. So we share something. Okay, that's where I wanted to be. So some more exercises for you guys. You're not escaping. We are still warming up. Even though the temperature has gone up outside, we should still warm up, because the neurons actually need this kind of internal warming up. Before, I gave you some regular expressions, and I asked you to do some reverse engineering for me. Namely, what do they mean? Now I ask you to do some regular expression programming for me. Let's look at the second block here and question 1. I want you to write a regular expression for me that is matched by the collection of all the bit strings of even length that start and end with a 0. Okay, so bit strings of even length that start and end with a 0. Okay, just a second, let me put the scratch pad up. And those of you who are at home, of course, stop the recording and do the exercise yourself before you get hints from your colleagues. Even though the spirit is strong, but the flesh is weak, so I would look for the hints straight away myself.
I think you should start with the 0.
Yes, you're supposed to do that.
And one of those brackets with the 0 or a 1 in it, after that. Like bracket 0 or 1. 0 or 1. And after that, there's a, because it has to end with the 0 as well.
Yeah.
There has to be a 0 after that. And the star at the 0 or 1.
Okay, so let's see. Okay, so let's look at this regular expression. And I apologize for the writing, but you know what I'm talking about here, what I was supposed to be writing about. So let's see. There were 2 requirements. Thou shalt start and end with a 0. And this is certainly met by all the strings that match this regular expression. Why? Because the regular expression says, thou shalt start with a 0, start with 0, and the other commandment that Moses brought with him was, thou shalt end with a 0. Okay? There was another commandment, though. Thou shalt be of even length. And now we are not quite there. Why? Because, as you can see, for instance, the string 0, 0, 0 matches this pattern. So all we need to do is to modify the pattern a little bit, the regular expression, so that it also complies with the requirement, thou shalt be of even length. Okay, so your colleagues here are saying we have to put any pattern of length 2 inside the start bracket. And there are several ways of doing that. Let's do it the simplest way. So, well, it involves some writing, but I'm doing the writing. You do the checking. Okay, so you repeat, you add in all possible ways bit of strings of length 2. This is supposedly some sort of ones. Sorry? Okay.
Is there a way to shorten this?
Is there a way to shorten this regular expression? Well, one way of doing this would be to say 0 or 1 followed by 0 or 1 inside the bracket, sort of, and then you take the star of that. That's shorter. It's the same. It has the same meaning. It's a sort of shorter. I haven't counted the number of symbols, but it looks shorter. And that's just because I'm, it's not a substantial gain, but anyway, it is shorter. Are you happy with this? Okay, so I assume that the silence means everybody's happy. So let's do another exercise. There you are. Let's try to do the second one. Then I leave you the third as an exercise for home or for the exercise session or wherever, whenever you're sipping a beer and you don't know what to do, you just write a regular expression. It works. So somebody is complaining about the beers here. No, the set of bit strings ending with a 1 and not containing 0, 0. Okay? Let's keep this in mind. Ending with a 1 and not containing 0, 0. There is a question. Yeah.
Okay, you start with a large bracket.
Okay. Start with a large bracket. I hope this is large enough.
Yeah, with a smaller 0 or 1 bracket in it.
With a smaller 0 or 1 bracket in it.
And a 1 after that.
And a 1 after that.
And then they close the large bracket. And star. And add a 1 at the end afterwards.
Okay. So remember what we wanted to do. I've just been a bad writing tool for one of your colleagues here who suggested this regular expression. Okay, what is it that we wanted to do? We wanted to have all of the strings of zeros and ones that end with a 1 and do not have the pattern 0, 0 in them.
But this one cannot generate 0, 1.
Okay, so one of your colleagues is saying, look at the strings 0, 1 and the string 1, 1. Say, do these strings match the specified pattern?
Can we put the star on the 1 inside the first bracket? And then the star after the bracket, so it's always 0 or any number of 1s, and then followed by 1.
Okay. There are several suggestions here. So you suggested that I would put...
Same as the first bracket.
Yeah.
Put star above 1.
Here. Here.
Where it right? No, inside the bracket. Yeah, and outside the bracket.
Inside and outside the bracket. Okay. Here. 1 star here. Or... Yeah, I mean, now this gets a bit cluttered. So perhaps let's start all over again.
Yes.
Let's start all over again. Okay, I want to end with a 1. So I put a 1 at the end. Now, before that, what I want to ensure is that I never see 2 zeros in a row. That's the thing that I want to ensure. So how do I write a string before that should be an arbitrary string that does not contain 2 zeros in a row? If I write a 1, that's okay. Is that right? So I could start the string by writing a 1. And this does not break the fact that I cannot have 2 zeros in a row. Or, okay, the other option is that I write a 0. But if I write a 0, what? It has to be followed by a 1.
0 and 1. 0, 1. And star.
Hmm? Star here.
Brackets.
Hmm. Okay. We are getting there. We are getting there. Does it always work? Okay, so we have something here. Okay, but we are getting there. Eh? Yeah, yeah, absolutely. We can't generate. So the string 0, 1 does not match this. Where? Sorry. Like this. Okay, so let me put parentheses to this ambiguity. Or so you see, so it's better if I get you to write this, I think, because so this is not what you had in mind. So I'll just rewrite what. Okay, so there was a 1 here. So what did you want me to do? Parentheses around.
So you could write 1, 0, 1 in the end. And with 1 or 0, 1.
Yeah, that's what I like this. Yeah, okay. Okay. So what now? Does it work? I think it does, but you can look at it at home. Yeah? It just indicates that sometimes it takes a little bit of iterations, a few iterations to get things going. Okay? Another possibility could be that instead, all
the secondary parentheses are necessary.
Writing
the same thing twice.
You mean is this parenthesis necessary? Well, there is an abbreviation for getting rid of this thing here, and this is the one followed by O1 plus. Plus means 1 or more iterations, not 0 or more iterations. And you're allowed to use this abbreviation supported by, for instance, the Automata Tutor, as well as many other things. So this is something that you're allowed to use wherever you find it useful, for instance, to reduce the size of expressions.
What symbol do we use instead of union?
What symbol? Oh, the question is what symbol to use instead of union in the Automata Tutor, and it's the pipe symbol. Anyway, the syntax is described on the Automata Tutor page as soon as you enter the regular expressions. Okay, so we've done some exercises. But now, I think there is a natural question to ask. The reason why people put forward the language for regular expressions was to describe patterns that automata can check. Well, how do we know that we actually have done the job correctly? In particular, there are two very important questions that I think we should address. First question has to do with algorithms, because we are computer scientists. We want to have algorithms to check stuff for us. And the microphone had decided to turn off itself, but I hope that my voice was being recorded by this thing. So suppose that I have a string W and a regular expression A. is there an algorithm to determine whether the string W actually matches A? And of course, you know that the answer must be yes. Why? Because you do it all the time. How many of you use Emacs? Oh my God. Nobody's raising their hand. What editor do you use? Vim. Okay, that's okay. But I'm pretty sure any editor that you use, you should use Emacs, by the way, but that's another matter. How many, I'm pretty sure that any editor that you use, a good honest-to-God editor, would allow you to do search by regular expression. Well, so obviously, that is possible because this thing actually implements this. That search facility implements an algorithm of this type. That's the first thing. The second question is, if you wish, perhaps even more fundamental to a certain extent. So I remember last time, one of your colleagues who's now sitting in the second row, for those of you who are at home, that's a very useful pointer, said, well, how about a pattern like XOR? You either match the pattern A or B, but only one of them, not both of them. Or how about a pattern AND? You have to match this pattern and this other pattern. Or how about a pattern NOT? You don't have to match. You're good if you don't match this pattern. Well, it looks like we cannot describe those in the language for regular expressions because we don't have AND. We have OR, but not AND. We don't have NOT, and we don't have XOR. So are we missing something? Well, fortunately for us, a guy by the name of Stephen Cole Cleany, whose photo you see on the slide, answered both these questions and many others in a fairly recent paper from 1956. In fact, he actually did the work in 1951 during a summer job at the Rand Corporation. So I'm just making sure that my voice is recorded by some microphone here. He actually, first of all, introduced the language for regular expressions, and he proved that regular expressions had the same expressive power as finite automata. And moreover, he did that algorithmically. That is to say, given any finite automaton, he showed how you can construct, by means of an algorithm, a regular expression that describes the pattern checked by that automaton, that describes the regular language that that automaton accepts. And conversely, given a regular expression, he showed how to construct from it, by means of a recursive algorithm, recursion, you shouldn't forget it, by means of a recursive algorithm, how you can construct a regular expression that describes the pattern being checked by the automaton. In particular, the construction from the expression to the automaton, the checks for the pattern described by the regular expression, is what is at the core of lexical analysis in compilers. And that's the one that I'm going to show you right now. The other conversion also exists, but it's more complicated, and you will have to take a different course to have a look at it. So, ladies and gentlemen, spider sense is tingling. You're going to see an algorithm, mostly by means of examples, but also by means of some general constructions, an algorithm that, given a regular expression, builds automatically a finite automaton, in fact, an NFA, because that makes life so much easier than if we had to build DFAs directly, that checks for the pattern described by the expression. Okay, ready? In fact, some of it you're going to do yourself, because some of it is not mind-boggling, and the rest is just programming with with finite automata, with NFAs. Okay, so how do we do it? The language for regular expressions is defined recursively. There are some basic regular expressions, the empty set, lambda, A, and then some recursion rules that tell us how to build composite regular expressions from basic regular expressions that we've already built. So that's going to be the recursive step of the algorithm. So the algorithm is going to be recursive and syntax-driven. You feed it with a regular expression, it will look at the syntactic form of the regular expression. For each one of the cases, it will do something and return the result. And for the composite cases, it will call itself recursively to build automata for the component expressions, and then it will combine them together to build a bigger automaton for the big expression. Okay? So, one step at a time. The base cases first. Okay? The algorithm will say, give me a regular expression. And then it will do a case statement or switch, depending on whatever your favorite language is. Is the regular expression that you gave me equal to this thing I just drew? And if the answer is yes, I can immediately spit out an automaton, the smallest one that you can think of, that actually accepts no string at all. Which automaton is this? Start state, which is not a final state. The algorithm terminates. Hey, I'm done. Fantastic. But this is not the only regular expression. What if you give me lambda as an input? What should I give you back? Well, basically the same automaton that we had before, but now the start state is also an accept state, and there is no outgoing transition. Because if I read anything, I'm not happy. I'm only happy with lambda. Third basic case. You give me an A. Now we're cheerleading here. Give me an A. Okay, so what do I spit out? An automaton that only accepts A, an NFA. What is it? Okay, start state, as your colleague is saying, one transition that goes to an accept state or final state, and the transition is labeled A. So far, so good, isn't it? But these are all the base cases. Now the R part starts, where the R stands for recursion. So suppose now that the expression that I'm fed with is of the form A union B, where A and B are smaller regular expressions. What am I going to do? Well, first of all, A and B are smaller, so I can call myself recursively. Now I'm the algorithm. I call myself recursively on A. And out comes an NFA that checks for the pattern A. I call myself recursively on B, and out comes another NFA that checks for the pattern B. Question is, how do I combine these two NFAs together to get a new NFA that checks for the pattern A or B? Okay, so let's look at a concrete case first, and then I will tell you how it works in general. So suppose that the recursion on A spits back for me this automaton that I just built right here for A. That's the automaton for, so the regular expression big A was in fact just small a. And let's assume that the regular expression capital B was just, well, you just have to match the pattern B. Okay, so these are the two automata matching the patterns A and B that I have. How do I combine them together? So these are, if you wish, pieces of library code that I got by recursion. I want to work with those. I want to combine them together to get an NFA that accepts A or B. Okay, so what do I do? Okay, so here I have two start states, but in an NFA I can have one. So I just add the new one. Okay, and your colleague is saying, now this new start state should be able to do everything that the start state of the first automaton can do, and everything that the start state of the second automaton can do. So let's change color, just to see that this is the new stuff that we built. Okay, so and I'll stop whistling here. And now what is it that I do? This is not a start state anymore. This is not a start state anymore. And I managed to erase also stuff, of course, that I should not have erased, but I can put them back. There you are. That's how the thing works in a nutshell. Whenever you have an automaton and another one, you build an automaton for the union of the two patterns by adding a new start state, and the transitions for the start state are inherited from the transitions of the old start states that you had before. The final states are just the union of the final states. There is one thing, however, that we have to take care of. Sometimes the new start state must also be an accept state. Not in this case, but it may be. So when do you think that the start state that we add should also be an accept state? When the automaton for A union B should accept the empty string. Absolutely, your colleague is saying that. And when is it that it should accept the empty string? When either A or B were matched by the empty string. That is to say, when either of the two automata had a start state that was an accept state, so the new start state should be an accept state. So if we call the start state for the automaton for A as A, and the start state for the automaton for B as B, and this new start state, we call it as new, then the rule is that S new is a final state if and only if either SA or SB were a final state. So this is final if and only if SA was final in the automaton for A, or SB was final in the automaton for B. Absolutely. Yeah. It's just that, you know, when I'm, for those of you who are at home and cannot follow all this stuff, now we do have some light outside. And since we don't like it, we're putting the blinds down. These are the joys of following the weather. Okay? So put the blind a little bit down. Okay? So far, so good. Now, question. Okay, yeah. The question is there any reason why we cannot actually remove the transitions that are not reachable anymore, actually, from the start state? There is no reason for keeping them. It's just that this makes the construction standard. You can always remove them afterwards because they are not reachable. In fact, you all know graphs. This is a reachability problem in graphs. You can remove all of the states that are not reachable because they are not going to make any difference whatsoever. Where reachable means reachable from the start state. That's another thing that computer scientists know how to do particularly well. But absolutely. So it's not necessary. It's just that I don't want to remove them. I'm just giving you the construction in general. There is no guarantee that the construction will be optimal. It just works all the time. Then you can make it optimal and screw it up. But that's, as Donald Knuth says, there's nothing worse than premature optimization. So let's not do it. Let's follow what he says. Okay, so it's time for a break. After the break, we are going to see how to cope with the rest of this construction. This